Today I'm going to be telling you about this concept of stabilization wedges that I've been involved in one way or another since it was first coined back at Princeton University in 2004. I've sort of added to the description and also updated it because the description that was originally created actually has been superseded by events in terms of world carbon emissions, and so you'll see that in a moment. That there are more wedges needed than were originally written about a few years ago in Science magazine. And I'm also going to back that up, since this is a sort of a big picture global vision of what's needed to stabilize climate, with a couple of practical examples as well. So this is the outline of my talk. I'm going to start by going over some of the basics of the carbon cycle and then explain the wedge concept. And then I'm going to end actually with a potential climate solution for California that I've been working very hard at recently, something that can be adapted well to the wedge framework, and I'll explain that if there's time. So this is one way to simply visualize what is going on in the carbon cycle, which is obviously an immensely complex system, but sort of to first order, you can think of it as a bathtub filling with water, okay? Where CO2 from fossil fuel emissions and other industrial emissions are slowly filling this bathtub, okay? And if the emissions are constant over time, that's what the graph of emissions looks like. But what's happening in the atmosphere is essentially the water level in the bathtub, okay? So that's slowly filling up. And the reason why it's filling up is because, well, there is a drain, except the drain isn't large enough in order to dispense all the water that is accumulating. And in recent decades, that ratio has been roughly 50% get reabsorbed by plants and the ocean surface, 50% stay in the atmosphere, and so you have a steady accumulation, a straight line that looks like this. Unfortunately, the real situation is worse than this because we don't have steady emissions, we have increasing emissions. And so in that case, you would expect to see accumulating concentrations in the atmosphere, which is exactly what's been happening, with still a roughly 50% uptake by natural sinks. However, that these in fact will be changing over time, and all model predictions suggest, at least for the oceans, that there will be a relative decrease in the amount absorbed, and perhaps with land plants too, although that's a much more complicated conclusion that's still being studied in scientific literature. So now I'm going to integrate this a little bit into what might be in our future. This is just one particular scenario, sort of, if you will, a median or a middle-of-the-road scenario from the various IPCC scenarios that were shown in the first talk this morning, where in red, we have increasing CO2 emissions. In 2005, it was slightly more than 8 billion tons of carbon per year. And in the next 50 years, these are projected to roughly double with a continued upward trend. And the resulting CO2 concentration in the atmosphere would then go from slightly less than 400 parts per million today to above 500, okay, with no end in sight. And I've only taken this figure to mid-century because things just get a whole lot worse. And one of the frameworks of this wedge analysis that I will share with you in a moment is that it doesn't make a lot of sense for us to look out much past 50 years for several reasons. When you show figures that go out to 2100 or beyond, the eye sort of naturally looks to the right-hand side of the figure and glaze over because the quantities are so enormous and so scary. And so the wedge framework limited itself to looking at the 50-year time horizon. And part of the reason for that is, well, things aren't as big, but it's also a level of time that most people can conceptualize, or at least with a little bit of a stretch of the imagination. Many of us who are starting our careers today, the younger people in the audience, will still be around and may be able to influence policy. Also, it's the lifetime of various structural components of our economy, such as the coal plant, which is built to produce electricity for 50 years or more. Not so much with some of the other elements like automobiles, but it winds up being a useful planning horizon. And so then the question that one naturally asks next is, okay, well, if this is business as usual, what do we have to do in order to stabilize CO2 in the atmosphere? And in a moment, I'll get into what that level of stabilization might be in order to avoid most of the climate catastrophes that we've been hearing about earlier. So here's the business as usual scenario, concentration and the, emissions and the associated concentration of CO2. Here is the path of emissions that one needs to take if we are to stabilize concentration somewhere near 500 parts per million, or probably below, actually, by the end of the century. Let me go back and show you. So what it means, essentially, is that today's emissions have to peak very quickly and bend over, essentially being no higher than today's rates by mid-century and dropping precipitously by 2100 with continued decreases beyond. Essentially, and I think the main point here, most of us realize that emissions have to drop, but it's not widely appreciated that emissions don't actually have to get to zero, okay? Because of the continual effects of natural sinks from the ocean and the land plants, there is some room to emit some CO2, although not very much, resulting in a stable atmospheric concentration, as I show here. Though this is a simple model, so we can debate, those who might know more about it, about various feedback mechanisms and so on. So the stabilization wedge picture takes this complicated carbon cycle model, the results of which I showed in the last figure, and simplifies it into a very straightforward, straight line cartoon, if you will, where instead of having curves, we now say, look, by rough measure, it really doesn't matter which scenario you follow exactly. If emissions double over the next 50 years, okay, which is the time horizon we're looking at, going from 8 in 2005 to 16, 50 years later, that's going to, and then continuing thereafter, that's going to result in about 800 parts per million CO2 by the end of the century, which is equivalent to about a 4 or 5 degree Celsius increase globally. To stabilize at a much lower and less dangerous, but not absent of danger concentration, we basically have to keep emissions constant over the next half century. Maybe going up at first, but then dropping down, and then afterwards with a pronounced decrease. Okay. This results, got the time delay here, essentially dropping emissions in half by 2100. And this creates then a mathematical quantity here, this triangle, which I have called the carbon squeeze, or sometimes called the stabilization triangle. It's the amount of carbon that needs to be kept out of the atmosphere over this next half-century period. Okay? And this is just an almost unfathomable amount of carbon, and is not really something that can be solved with a single given technology. It's going to require, and this is on a worldwide basis, worldwide effort and many overlapping technologies. So we take this enormous amount of carbon and break it into a number of wedges, and there's the wedge term being introduced. The original Sokolow and Pakala paper had posited that 7 wedges would be needed to stabilize emissions over the next half century, but that's because they were assuming that we would only be at 7 in 2004. They wrote their paper based on 2002 data, and it looked likely that that is where we would be globally. Turns out that in 2004 we were at 8, and we're higher than 8 billion tons already. So I've revised this to start at 8 billion and going to 16 instead of 7 to 14. Therefore you have 8 wedges, but it's more or less the same magnitude of the problem that was originally described. And so now the question is, so now we have the problem broken into 8 pieces. Great, how big are each of these pieces, and what do they sort of mean in terms of real world solutions? So a wedge is defined here as the avoidance of 25 billion tons of carbon over a 50-year period. In other words, going from avoiding nothing at the starting point to avoiding 1 billion tons over the 50-year period. The area under this curve is therefore 25 billion tons. I also express it in tons of CO2, which are units more familiar actually to most people these days. It's about 100 billion tons of CO2. Okay. Now that's in terms of the CO2 being released, but what does it mean in terms of actual practice? Well, there are a lot of solutions that, of course, remove carbon or avoid carbon in the atmosphere, but these are the criteria that are needed to qualify as a wedge. One is that it has global scope. It's not just applicable in one corner of the world, but can be applied over a large swath of countries. That it can be sustained over a 50-year time horizon. It's not something that you build once and then you're done. You have to keep building over time, and I'll explain more of that in a minute. We're using simple shapes just for illustrative purposes. Of course, they could be more complex in the real world and probably will be. And this is really, the last two are really important. One is that there is a potential worldwide to avoid at least 1 billion tons of carbon after a 50-year buildup. There are some technologies that appear really wonderful in avoiding carbon and producing fossil-free energy, but they just aren't big enough to scale up to the worldwide stage. And if I can remember an example of one of those, I'll mention it a little later. There are a lot of small players, but there are fewer large players, and these are the ones that are really going to help to drive down this carbon problem and solve it. And finally, there are a lot of commercial scale technologies that are available right now to solve this problem, and we're going to need all of them. We may also need some that are not yet ready for commercial deployment, and those are intentionally left out. Not that we don't think that nuclear fusion research is a good idea, for instance, or space-based solar energy, but they're just not really ready for commercial deployment, and therefore they aren't considered a wedge. Maybe it will be a wedge to be deployed in the second half of the century, hopefully sooner, but that's not considered a wedge in this way of thinking about the solution. So now, briefly, what is dangerous interference? We had a very nice talk this morning by Terry Root, who went into this a little bit. I've picked 2 degrees Celsius change from the pre-industrial level as kind of the best that we can hope for. Honestly, I think that we need to aim a little lower. I just don't see that as being technically or economically feasible at present. Perhaps we'll be able to crank down the target over time. But it seems as though 2 degrees C is the confluence between where risk really starts to take off and look very dangerous, and also the place where economic impacts are not considered devastating. And so the European Union, for instance, has chosen 2 degrees C as their target and are gearing their policy toward an overall worldwide stabilization at 2 degrees. And I'm going to be using that too. So then the question is, what emissions pathways correspond to a temperature change no more than 2 degrees C? And this is a complicated figure. I'm not going to go through this. This is essentially a meta-analysis of a number of high-level carbon cycle models and associated climate models, looking at what the probability of reaching worldwide global temperature change is for a given level of CO2 in the atmosphere. And what I'm drawing your attention to here is the probability bounded by all of these models has an average of around 50% for a stabilization level of 450 parts per million CO2. And what this means is that if we are much higher than 450, then the probability of going higher than 2 degrees is much greater than 50% chance. Whereas if we aim lower at or lower than 450, then we have a greater chance of not exceeding 2 degrees C. But unfortunately, the models are just not that good. And I'm not sure that they will ever become good enough to say with certainty what our temperature change will be. But in an average way, at least this gives us a ballpark to shoot for. And so I'm adopting 450 parts per million as the target that we need to aim for. So now, when the stabilization wedge model was first introduced 4 years ago, the authors had chosen 500 ppm as the target level, and that was because at the time the literature was debating a higher level, thinking that that was safe, and the discussion was really between 450 and 550, so they picked 500 as sort of a median good enough goal. As it turns out, as I just showed, that's looking like it's on the high end, and so taking that goal down from 500 to 450, a 50 ppm difference, makes a huge difference to the target level that you need to achieve globally. Now we're looking at not maintaining constant emissions, but dropping them in half over the next half century. resulting in 12 wedges, with further reductions through the end of the century, basically dropping in half as well. Okay, so this makes the problem quite a bit larger, more challenging, but again, not impossible. Now, the story isn't over, and I need to also emphasize this because in most discussions of climate change, there's a huge glossing over of the non-CO2 climate forcings, the methane, nitrous oxide, halocarbons, and other agents that also cause warming. And so I put together this figure to illustrate the difference between looking at just CO2 and when you consider everything together. And the 2 points here is to say that the other agents, these gases, and then also things like aerosols and other particulates that, by the way, have both negative and positive forcings, the different species, but a net negative. It definitely increases the overall, but it's only a little bit larger than that of CO2 alone, and is why a lot of discussion in the literature kind of interchange the two, because the amount of forcing, how much heat is being trapped by the atmosphere net, is not that different. However, looking forward, assuming a reasonable scenario of the increase in all of these agents, there will be an additional warming due to the net effect of these gases above that of CO2 alone. This is the scenario that I had showed a little while ago. And so we have to include those other gases in our stabilization framework as well. It's 2.2 degrees according to the model that was used to generate this by the end of the century. And so when we add these others, oh, and I forgot to mention also, there's deforestation as another source of CO2 that's very important. You add methane, nitrous oxide, and halocarbons, you add another 5 billion tons of CO2, of carbon equivalent to the mix. And then in order to get down to this reasonable level by the end of the century, you essentially have to reduce even further. And so the resulting number of wedges is now ballooned again to about 17.5. Okay, by my arithmetic. So this is becoming a much more challenging problem than originally presented. And so the message is really that we're going to pretty much have to pull out all the stops in terms of technologies that are available, as well as develop additional ones, and quickly. This is just an illustration of what that 2 degrees C stabilization scenario looks like, where basically each of these things is dropping in half by mid-century and then half again by the end of the century, with the final emissions of only 3 gigatons of carbon compared to 13 today. So now, what are some of those strategies? That's what I'm going to spend the second half of my talk discussing. There are a lot. Some of them have been already discussed by the previous speakers, like energy conservation and increased renewable electricity. A lot of these, I think most of you in the audience are already familiar with, and I'm not going to go through these exhaustively, but simply to illustrate the number that are available as outlined by Sakalau and Pakala and augmented by others. The point here is that each of these wedges illustrated in this pie chart is 1 billion tons of carbon avoided after 50 years. Okay? And if you look at the fine print, you can see what it takes in order to achieve one of those wedges. And I'll read one of them. It means increasing the fuel economy of 2 billion cars, about 3 times the amount in the world today, from 30 to 60 mpg. Average today is about slightly under 25 mpg. So it's looking at kind of future circumstances and saying that needs to double. That will be a wedge. Or reducing electricity use 25% worldwide is another wedge. This is energy efficiency and conservation. There's also more efficient power generation wedges. There's at least 2 of those. There's at least 3 wedges of carbon capture and storage from fossil fuel plants, mostly coal, to make hydrogen and fossil fuel-free electricity. There are a wide number of alternative energy sources: wind, solar, geothermal, ocean energy, and so on. And then some wedges from absorbing carbon through forestry and land management practices. One thing that's nice about this wedge framework is it doesn't just look at energy, but it also can look outside and say, look, just in terms of how much carbon we're avoiding, what are some of the trade-offs and what things are really able to scale up to the global scale. And then finally, we have 3 others which are looking at these non-CO2 gases, methane, N2O, and other gases. And there's probably more than 3 of these, but I wanted to be conservative and only assume that you could get 3 out of them. And this would do the job, but of course you'd have to deploy all 18 of these in order to achieve. I will say, however, that some of these wedges There's more than one of them available. In other words, you can build, and I'll show you in a moment, you can build a wedge's worth of wind turbines in the world. You can actually build 2 or 3 if you really wanted to, and with the associated savings therein. So they can sometimes substitute if other strategies turn out to not be feasible on a global scale. They're either too expensive or technically too challenging. But I think the message is that we have to be working on other technologies as well, and quickly. So I'm going to give 2 examples. What does a wedge of wind substituting for coal electricity look like globally? And there's 2 ways to picture this. One is how much needs to be substituted each year, again assuming kind of a linear increase, and then what's the overall 50-year horizon look like. So what this means is that you need to not build about 14 gigawatts of coal, which is about half the yearly increase worldwide. So it's about 28 500 megawatt coal plants, and replace them with 40 gigawatts of wind power, which is about 3 times the current rate of expansion of wind worldwide. Okay? And that's not impossible. That's not that much faster than where we are today. And again, this is a linear increase over 50 years, so it can start out a little slower and then ramp up after adequate policy are in place to encourage it. After 50 years, what this would mean is that about half of the current capacity of coal globally, 700 gigawatts, is not built, and instead 3 times that capacity of wind is built in its place, which is about 30 times what is on the planet these days. Now, question mark might come, well, why do you need 3 times the amount of wind power as coal power? And the reason has to do with the fact that the wind doesn't blow all the time. And so in terms of the number of kilowatt hours generated over a given period, a year or so, a coal plant can push out many more because it's mostly running. You know, about 85, 90% of the time it's on, whereas a wind farm maybe produces 35 or 40% of the time. So we assumed a 3-to-1 ratio in our simple illustration here. So that's wind. You can use your imagination and imagine similar situations for the amount of, say, solar energy that would have to be deployed. There's land areas to worry about, but there's certainly plenty of resource out there. And to show you the, I'm going to skip through this rather quickly. These are the forecasts versus the actual growth in wind energy worldwide over the last few years. It's looking like we're exceeding the forecasts, at least from 2004. And in terms of global electricity generation, to put this in perspective, this is a pictorial illustration of how much electricity is being produced from all sources worldwide in 2006, about 18,000 terawatt or trillion watt hours of electricity. By 2055, conservative estimate is that this would roughly triple to 59,000 terawatt hours. But the global wind potential is estimated by some colleagues of mine at Stanford, Mark Jacobson and Christina Archer, estimates about twice that amount of potential worldwide to be developed after excluding a large percentage of this for competing land use and so on. So there's plenty of wind resource out there if issues of intermittency and reliability and energy storage are all addressed. The amount being produced right now is represented by this orange square, and a wedge would be the yellow box. So there's more than enough wind energy, at least. Solar looks even better, but it's really the cost issue there to produce the energy that we need without burning fossil fuels. Just illustrating what happens when you add 1 wedge of wind to take a bite out of coal, that there's plenty of room left from other resources that can displace the remaining coal and gas that are producing CO2 emissions in a potential electricity mix 50 years hence. Okay, so the second example I wanted to go through is what does a wedge of efficient cars look like? And I mentioned that a couple of slides back. What that would mean is replacing about half of the current global sales of automobiles from a 20 mile per gallon car with a 40 mile per gallon car represented by the current generation of Priuses, which is 80 times the current Prius sales worldwide. That's every year for 50 years. After 50 years, what it would mean is that all 2 billion cars, we have about slightly less than 1 billion now. I think at last count it was close to 800 million. assuming 30 miles per gallon average now, it's close to the 35 mpg target that the US recently put forth, and instead everybody's driving a 60 mile per gallon Prius, okay? Every single person in the world. Now this is an average, so what it means is that some cars will be less efficient, but there are going to be some cars that are phenomenally more efficient or maybe aren't burning gasoline at all. Of course, that's another wedge, is replacing gasoline with electricity or hydrogen. But that's what it's going to take in order to get one wedge out of the transportation, personal transit sector. So, you know, this is achievable. This is achievable with current technology, as is a criterion for the wedge framework. And it can be done through a combination of different factors like hybrid engines, better aerodynamics, lower rolling resistance tires, more energy efficient appliances on board, which results in a smaller engine, and so on. And I love this one, cool paints. Did anybody realize that if you paint your car with colors that reflect most of the infrared, you don't need as big of an air conditioner, and then you don't need as big of an engine, and then you don't burn as much gas. You can get a savings of several percent just by painting it with an IR reflective paint. So this can get our first wedge. What about getting that second wedge out of personal transit? Well, that would need more sophisticated technology, such as plug-in electrics, biofuels to actually reduce the amount of carbon in the fuel itself, and of course less traveling in the first place, which can be achieved through a number of innovative approaches. The main thing, of course, is building urban structures not so far away so that people don't have to commute as much and travel by car to do their errands. But these are a lot harder, which is why it isn't often discussed as much. I think the point here really is that there's a maximum of 2 wedges to get out of the transportation sector, unlike the electricity sector that had many, many more available. This is pretty much all the carbon that there would be after 50 years. And this is an illustration done a few years ago now by the Sustainable Mobility Project, which shows the projected increase in energy use, but I've scaled it to sort of what the gigatons of carbon would be. It's about slightly less than 2 gigatons today, probably doubling in 50 years. And this is not just cars, but all transportation. So it's including air, water, and freight trucks. And so as you can see, 2 can be removed by focusing on cars and SUVs, but there's 2 more if you can focus on the other elements of the transportation structure. However, I think that's more challenging. Not impossible, but more challenging. Maybe we can get 1 more wedge out of here, but probably not 2, without some very clever ideas. So, as a final example, I'm going to share some work that I've been doing looking just at the state of California, and I share this for 2 reasons. One, I'm excited about it, and it's a bit more detailed than the treatment that I showed you before for the world as a whole. It's easier to focus on just a particular state. Secondly, I wanted to illustrate how the wedge concept can be scaled down to a particular small area and is still a very useful concept. So, as most of you probably know, California passed a landmark Global Warming Solutions Act in 2006, which mandated a reduction in statewide greenhouse gas emissions back to the 1990 level by 2020. We're around here at 500 million tons of CO2 equivalent today, and we were around 430 back in 1990. Okay? Business as usual would project that we'd increase to maybe 550 or so. So we're talking about a teeny wedge here that needs to be produced. However, there's another data point here. That only looked out to 2020, and around the same time that that law was being debated, actually the year before, Governor Schwarzenegger announced that California will strive to achieve an 80% reduction below the 1990 level by 2050, which is actually just about spot on in terms of where we need to go, certainly in developed countries like the United States that's been producing the lion's share of greenhouse gas emissions. So I just took this mandate and assumed that that would be part of some kind of future legislation, and then looked at what sorts of technologies were available to meet this in California. And so you see that it's actually a slightly steeper curve, but it's more or less a continuation of this same downward trend here to 2050. Okay. And what this does Okay, I already told you this. So it's a 22% reduction by 2020 from business as usual and 80% below by 2050. This is actually more like 90% reduction from where we would otherwise be. So what I did is I defined a California wedge, which is 1/60th of a global wedge, because California, it turns out, emitted about 1/60th of global CO2 pollution in 2004. And to meet the requirements of this law, you'd need just over 12 California wedges to do the job, okay, each one being about 50 million tons of CO2. And so I built a model and have a solution that can get us most of the way there. And you can't read this, and I'm not going to read it to you, but the point that I wanted to make, first of all, is to show you that it is possible through a combination of solutions to get to an ambitious target like that. The other thing I wanted to say is this was really done in a very thoughtful way, sector by sector. So it wasn't just sort of throwing solutions out there until you got down to zero. It was looking first at the transportation sector and saying, what reasonable amount of improvement in fuel economy could we squeeze out of these different categories like personal transit, freight transit, air travel, and so on. And then on top of that, how much biofuel could we grow in the state of California to supplant some of the petroleum use? How much conversion to diesel cars from gasoline could we build? What about plug-in hybrids? What percentage of the vehicle fleet could conceivably be replaced that way? And all these things were then superimposed so that you had a solution that was built out of multiple technologies. And we did that for each of the sectors. And we came up with the idea, thank you, that you know, with some ambitious but not unreasonable goals, you could get most of the way there. I'm happy to talk more about this if people are interested, but I just wanted to illustrate that the framework works. And it's essentially just building things out through 2020 and then continuing the improvements thereon. So if you have a 10% improvement in energy efficiency by 2020, then it's a 40% increase in efficiency out by mid-century. And that is supported by various studies on energy efficiency, looking at the long-term potentials, for instance. So here are the optimistic conclusions of my talk. You know, one is that I feel that severe climate change is probably avoidable with the political will and the technological ingenuity properly harnessed. But climate change itself is already here, and so it's not completely avoidable. And there's probably worse to come, and there will be some adaptation needed, not only for human beings, but for species, as we heard by Terry earlier. That we're going to need very large reductions in greenhouse gas emissions from where we are currently and where we're headed. Probably 80% below current. However, the solution is not a single technology or a single policy. It can be broken into smaller problems that are challenging but not intractable. Although I should add here that, of course, international cooperation is necessary. The United States, after all, only produces about 20% of global greenhouse gases now. So even if we got into gear ahead of everyone else, sort of an absurd hypothesis, but if a nation as large as the United States were to get very serious about climate change and nobody else did, it really wouldn't make much of a difference. Psychologically, of course, it would make and will make a tremendous difference because we are world leaders and we do need to lead by example. And so it's very important that we get out ahead. But clearly, international cooperation is absolutely necessary to solve this problem. Nobody can do it by themselves. And that deep reductions are possible on the smaller level, as I show the state of California. So I'm actually giving you the gift of a few more minutes. I'm stopping early, but happy to take your questions now. Thank you.
What about the argument that all your efficiency and conservation wedges will just increase the size of the economy, therefore you get nothing? I save $5,000 in gas, I buy a big flat screen from TV, they build another plant.
Sure. So just make sure everyone heard that. What if all the efficiency measures are outweighed by increased consumption? And that's a valid point. And, you know, we don't have a I would say, a tremendously informed handle on just how much it's called the rebound effect, when when the calculated savings are not really what you get because of this increase in consumption. The literature that I've read suggests that the rebound effect does not completely outdo what you're trying to achieve with efficiency. And that is something that I have not modeled in this treatment because I don't have an economic model working as well that responds to these changes and so on. So I mean, the way to answer it in policy is to set targets that, if not achieved by year X, means that you then have to increase your target for year X plus Y. And you're going to get there through a somewhat torturous path. I mean, this is all a learning curve. Nobody's been able to achieve these deep reductions throughout their entire economy anywhere. And it's going to be a collective learning effort. But I think the point is that you have to set ambitious targets and then try to meet them, and then revise your goalposts as necessary, but make sure that you're still responding to science and achieving the levels of reductions that are really necessary worldwide. But thank you very much for that comment.
We have a question here.
We're waiting for the mic. Okay.
I'm thinking about war, peace, and the energy and material costs thereof. Would fewer and shorter wars be an energy wedge?
It'd be a wedge? Absolutely. I don't really have a comment. I think you said it best. These scenarios do, include petroleum consumption by military operations. Yeah, less of that would certainly help the situation.
All your wedges are continuous.
Where are you? Oh, yes, hi.
Would it be possible to have a discontinuous policy, for instance, no more new coal plants, and then fill in the gap by the continuous policies which you have been discussing in your wedges?
Yeah, I like the idea of no new coal plants. And in fact, that seems to be playing out, at least, well, it's hard to say. A lot of new coal plants in the United States have been scrapped in recent years. I think the TXU buyout was one of the first shoes to fall. I'm not sure that that's going to be sustained and that there will be no new coal plants built. It's a wonderful idea. From a political strategy point of view, however, I think it's a mistake to completely shut coal out of the debate, as it were, out of the solution space. I'm not an advocate for carbon sequestration, nor am I a skeptic. I think that it's a very promising technology that ought to be fully pursued, and if so, it would allow the very powerful, coal industry to continue to play a part as a real energy solution. My political strategy friends, I'm a scientist, so I don't really weigh in on these things, but the strategy friends that I work with tell me that to exclude such a powerful component of the energy system like the coal lobby would be a big mistake, because all they will do is fight back harder and make it very difficult to get anything done. So it's better to invite them to the table. But what I would say is phase them out quickly and over time. If we can achieve no new coal plants in the United States and worldwide, that would be great, but I'm a little skeptical about that happening in places such as China, for instance.
We have a question to your left.
Thank you.
Yeah, I heard you using California as an example of possible smaller scale solutions or looking at wedges. Is there a way to design some way to do that, maybe on a business level or on a school level as a teacher? I'm wondering if that's something you could do as an exercise in looking at how this works in a macro or micro scale as opposed to such larger scales.
Yeah, that's a great idea. Actually, a couple of people have approached me with the idea of, can you build sort of a household wedge picture? And I haven't done it. I think it's possible. It really does scale down to just about any level where you're looking at consuming, fossil-intensive energy in different sectors and how much can be squeezed out. So I would say, yes, maybe let's talk afterwards and point you in the right direction. It's a great suggestion.
Time for one more.
Let's see, I don't know who had their hand up last, but latest. He's got the mic, okay.
Have you figured population, shall we say population levels in your forecasts? And do you think it would be viable to try to reduce population and reduce immigration in the United States as a way of helping to stabilize the climate?
You know, thank you. I've long been a fan of good, sensible, non-offensive population policy, but when I bring it up, I find that it stirs a lot of people the wrong way. So I've tended to leave it off of these discussions, but I would say absolutely. To answer your question briefly, yeah, population increases are certainly embedded in this model, and the IPCC scenarios that we saw this morning, which has this huge fan of future emissions, the high levels are usually associated with higher levels of population growth and the lower, obviously, with low. This was a middle of the road sort of assumption, and it actually wasn't based on a model per se, so I don't know what the population growth assumptions were. But it's certainly true that one can reduce population in one's country by basically increasing the economic livelihood of the citizenry, as well as promoting equality between the sexes and giving good free education and things like that. And that would certainly bring down levels. So I appreciate the comment. Maybe there's a wedge in there from good population policy as well. Okay. Thank you. I'm afraid we're out of time. So.